let's talk about the concept behind this a little bit. And quantum physics, the name always seems to get people, they think, real outlandish things. We'll say that. And what we should remember as physicists is that quantum is merely referring to quantized. Quantized, that's where the name comes from. Now we're going to see that it's quantized in the sense of atoms, or very small particles, having discrete energies. So they have very discrete properties, and it's not a continuous set of properties. They are solid values. So they're a quantity. And that's where the name comes from. Let's talk, as a first point, about 20th century problems. So leading up to the 20th century, physicists had a great deal of solidity in all the classical things and a rather new physics that just popped up, or a new addition to physics, and that was special relativity. Relativity in general, because I think it was a decade later Einstein formulated his general relativity. That is the general relativity part, an incredibly complex area of physics. And in fact, if any of you are going to be physicists, that's not a class that you'll take until you're like an upper level graduate area. It can be pretty tough, pretty challenging. That was all fine for physicists around the world. The problem was that there were questions that they couldn't answer using the classical physics that they had. There were something else that had to be out there. But before we talk about that, let's look at the problems themselves. The first one is black body radiation. Has anybody heard of black body radiation? I wouldn't expect you to have heard of it, but you never know. I always like to ask. This is simply electromagnetic radiation. I'm going to abbreviate that EMR, so I don't have to keep writing it out. Emitted from heated materials. Yes, you may. So at the time, when you heated something up, I guess I shouldn't say at the time, but we still do this. When you heat something up, it actually emits light in various wavelengths. And in fact, you are, right now as you're sitting there, it's not a wavelength that we can see with our eyes. And we're actually going to do an example that will calculate the wavelength of the light that you're emitting right now because you are warm. So the problem was that didn't make sense from the classical sense of what's going on here. And we'll see that in detail in a second. The second one was the photoelectric effect. Have we heard of this before? Photoelectric effect. That's okay. Yes, I didn't expect you to, but you never know. The photoelectric effect is when you have, I did say electrons, okay. Emission of electrons when light is directed at metal. So you could take a light source directed at a metal plate of some variety, maybe hook it up to a circuit, and you would find that there is actually a current flowing through there just from shining the light on the metal. That's called the photoelectric effect. Again, that's unusual. It doesn't seem to match exactly what you would expect from the classical. Kind of, but that's an interesting observation. The last problem was something that we're actually going to see. We're going to actually look at this. Sharp spectral lines of gases when a current is passed through them. So let's say we take the noble gas neon. You see neon in signs all the time. If you take a device, say like a prism, and you break up the light in there, so you hold up a prism so it absorbs the light coming from the lamp or the tube, and you look at the light, you won't see a continuous spectrum of color in there. You'll find these very distinct lines of some exact wavelength, and each gas is a characteristic quantity. And if there wasn't some quantized distinct part in there, you would see the spectrum there. You would see a continuum of colors inside. That's not what we see. We see these distinct bands. And in fact, if you zoom in on those bands even closer, you see that they themselves are made up of smaller distinct bands. And this is where we get our ideas, if you recall, maybe from chemistry, where we have quantum numbers and magnetic quantum numbers and whatnot. That's where they come from. This was actually discovered, if I'm not mistaken, by Niels Bohr. And he discovered this, I believe, right after he got married and before he was supposed to go on his honeymoon. And he was so excited about this that they postponed their honeymoon so he could write this paper. I believe he won a big prize for that. All right. Let's talk about blackbody radiation. We'll tackle the first one. Blackbody radiation. Every object emits electromagnetic radiation when heated. What we find is that at low temperatures, it tends to be in the infrared direction. Of the electromagnetic spectrum. I put an S there. Basically what we're saying here is that this occurs in a range that's not visible to our eyes. We only see a small range, if you remember from your science classes before this. At high temperatures, we see a shift to red. It starts to glow red. You know, when something gets hot, it starts to glow bright red. And if you keep heating it, it'll turn white eventually. In fact, it goes like red, white, and blue. It's really, really hot. So there's something going on here where as you increase the energy, you're seeing the light that's emitted is changing in a wavelength as well. And we have a nice graph here that we can draw that shows some different spectra that we So if we put our wavelength down here in the bottom. This is micrometers. Micrometers. And this axis here is our intensity increasing in that direction. Intensity, can you read that? Intensity. So our red line here corresponds to around 2,000 Kelvin. Our green line corresponds, I believe it's something around 4,000 Kelvin. Oh no, that's 3,000. 3,000 Kelvin. And our blue one is 4,000. So let's look at what we see here. As our temperature increases, we see a rise in the total amount of energy. The area under the curve here represents the amount of energy that's inside there. And we also see that as we increase our temperature, the peak, I didn't draw this quite as well as I should have, but the peak wavelength shifts toward the smaller end. So the wavelength of light gets smaller. Which means that if we started red, for instance, we're going to be going in the blue direction as we go that way. Now we should take a minute here before we get too far along and away from ourselves to talk about what a black body is. In an ideal situation, it would be some device that has a small opening. Doesn't matter what the texture is on the inside of it. And we could have some light that comes in and then bounces off the various surfaces inside here. In other words, all of the light that's going in is absorbed by the black body. And any light that comes out of the opening, any emitted light, only related to the material that's being heated and no outside sources. So when we heat up this black body, when we add energy to it, say at a lower temperature, the light that's coming out will have a certain wavelength, it will have a small intensity. As we heat it up some more, we get a shorter wavelength that's coming out, more energy inside there. If we heat it up a lot, we see a lot of energy that comes back out, and the wavelength is smaller still. Quite tiny. This leads us to our first equation here. Wines or vines. I think it's from this place. I'll double check out on that. Yes, this place. I was wrong. I shouldn't doubt myself. it down and then talk about it. These comments. 289. Alright, so what his law says is that the maximum wavelength associated with some temperature is equal to this constant. So as we increase the temperature, and if we were to find the max wavelength, so we would be dividing this number by a bigger and bigger number, it means our wavelengths are getting smaller and smaller and smaller. Has anybody ever looked inside of a hot kiln before, like in art class?
Yes.
Like glowing,
when it's on?
glowing, yeah.
Yes.
It's like glowing red in there?
Yes.
Do you find that it's hard to discern the objects that are inside?
Yes. There's a bunch of.
It's hard to see what you're looking at as opposed to when it's cool. And that's because as you're increasing the temperature, the wavelength is getting shifted into a range that your eyes can't pick up very well.
Is it the same thing like if, when the sun's like hitting the hood of a car and you can see like the heat waves coming off of it?
Not quite the same phenomenon. No, because we're actually talking about matter that's glowing.
So yeah,
It's really hot. It's really glowing.
Oh.
If you made
Don't worry. I think I have a battery. Or,
20 minutes left.
there we go. It's happy. It's happy now. Alright, let's do an example. And then we'll call it quits for today. Alright, so thermal radiation from the human body. I'm going to need more space. Yeah, cool. Alright, so skin temperature is approximately equal to 35 degrees centigrade. So right now, roughly speaking, everybody in here is about 35 centigrade. What wavelength of light is emitted at its peak energy? What should I do? What am I looking for? So I'm looking for lambda mass. I know my temperature, 35 degrees centigrade. We know that's equal to our constant. Simply solving for lambda here, we would get 9.41 micrograms. Kelvin.
Oh, okay. So that's
So you would have to convert this to Kelvin.
okay.
So this is in the infrared. So right now, all of you, roughly speaking, are actually emitting light at this wavelength. And this is why if I use special goggles that allow me to see heat, I can actually see this coming off of you. Questions? All right, we'll wrap it up there for today.